Welcome back, everybody. Today, we're going to take a deep dive into gravitational potential.
Ooh, that's a good one.
Yeah, it's pretty fundamental to how our universe works. And to help us unpack this, we've got some excerpts from a website called
Okay.
Open Educational Resources, Open Source Physics at Singapore. And
From Singapore.
yeah,
Yeah.
and they even have interactive simulations, which we'll get to later.
Yeah.
But first,
Yeah.
think about this. Have you ever wondered how much energy it would actually take
Hmm.
to move something against gravity's pull? Like all the way from here on Earth to outer space.
Oh, wow.
That's what we're going to explore today.
That's pretty amazing. I mean, that's a lot of energy
It is, yeah.
to think about, you
Yeah.
know?
Right.
It's interesting you bring up moving things against gravity
Well,
because that really gets at the heart of what gravitational potential is all about.
okay.
We often think about gravity as
Yeah.
this force that pulls things down, but gravitational potential helps us understand the energy involved in moving something within a gravitational field.
So it's not just about force, it's about the energy tied to a location
Precisely.
within that field.
It's like an energy landscape of space, almost like a map
Okay.
that tells you how much energy you need to move an object from one point to another.
Okay, that's a cool way to visualize it.
Yeah.
So let's say we wanted to move a rocket from Earth's surface to a point way out in space.
Okay.
What would the gravitational potential tell us?
It would tell us how much energy we'd need to invest
Okay.
to overcome Earth's gravitational pull and reach that point.
Okay.
And it's represented by the symbol
Okay.
pronounced phi.
Phi. It sounds almost mystical,
Kind of.
like some ancient secret code of the
The
universe.
secrets of the universe, yeah.
So how do we actually calculate
Yeah.
this gravitational potential?
There's an equation for that, of course.
Okay.
It's equals negative gm over r.
Hold on. I'm seeing a negative sign in that equation.
You are.
Does that mean gravitational potential can be negative?
It does.
What would that even mean?
That's a great observation. And yes, gravitational potential is always negative.
Okay.
It might seem counterintuitive, but it all comes down to how we define
Okay.
the 0 point.
0 point. What do you mean?
We set the 0 point for gravitational potential at infinity,
Okay.
meaning infinitely far away from any mass.
Okay.
Think of it like a reference point.
Okay.
As you move closer to a mass like the Earth,
Uh-huh.
the potential becomes more and more negative.
So the closer you are to a massive object,
Yes,
the more negative the potential.
that's right.
Almost like you're going deeper and deeper into a well.
That's a great analogy.
Okay.
A negative value simply means less than 0,
Right.
signifying that you're in a kind of energy debt compared to that 0 point at infinity.
So if we were to lift a rocket from Earth's surface,
Uh-huh.
we'd be working against a more negative gravitational potential
You would.
than if we were already in orbit, right?
Exactly. And that's why launching rockets from the surface requires a tremendous amount of energy.
Yeah.
You're essentially trying to climb out of a very deep gravitational well.
Okay, so far we've been talking about moving rockets, but this
Sure.
energy landscape idea,
Yeah.
does it apply to everything?
Absolutely. It applies to anything within a gravitational field.
Wow.
From a tiny feather
Okay.
to a giant planet,
Wow.
everything experiences gravitational potential.
But wait, wouldn't a feather have much less potential energy
That's a brilliant point.
than, say, Mount Everest, even if they were at the same altitude?
That's a brilliant point. And it leads us to another important equation.
Okay.
U equals m. This equation links gravitational potential
Okay.
to the concept of potential energy, U, which is the actual energy an object possesses
Blah.
due to its position.
Okay, I think I'm starting to see the connection here.
Okay.
So you're saying a feather at the top of Mount Everest has ridiculously tiny potential energy
Yes.
compared to the mountain itself,
Yeah.
even though they're the same potential.
Precisely. The mass of the object
Right.
comes into play when calculating the potential energy.
Right.
But the gravitational potential at that specific location,
Yeah.
high up on Mount Everest, would be the same
Right.
for both the feather and the mountain.
So it's like the potential is a property of the location,
Yes.
and the potential energy is what that location does to an object with a certain mass.
That's a great way to think about it. And what's even more fascinating is that the mass of the object being moved
Okay.
doesn't actually affect the gravitational potential itself.
Really?
Only the mass of the source, like the Earth in this case, matters.
Hold on, are you saying a feather and a rocket at the same altitude
Mm-hmm.
need the same energy to escape Earth? Something doesn't feel right about that.
It might seem counterintuitive,
Yeah.
but remember we're talking about gravitational potential, not potential energy.
Okay.
The potential is all about the location. Within the field itself, not the object placed there. It's a property of the field, not the object within the field.
Okay, I'm going to have to let that sink in for a bit. But it's definitely sparking my curiosity. So if the mass of the object being moved doesn't matter, how does the distance
Okay.
from the source mass affect the potential?
That's a great question, and this is where the inverse relationship comes in.
Okay.
As the distance from the source mass increases,
Okay.
the gravitational potential gets closer to zero, but remember, it's still negative.
So even though it's increasing, it's still negative. It's like climbing out of that gravitational well,
Yeah.
but you're never quite reaching the surface.
That's a great way to visualize it.
Okay.
And this is where that interactive simulation from the source material comes in.
Oh, yeah, I was wondering about that.
Yeah.
Tell me more about how this simulation works.
The Open Educational Resources Open Source Physics at Singapore website actually has a JavaScript applet that lets users play around with these concepts. You can manipulate variables like distance and mass and see how the gravitational potential changes in real time.
So you can actually see how the numbers change as you move further away
Exactly.
from the source mass.
It's not just equations on a page. You can see how it works, which
Right.
can be really helpful for understanding a concept like this.
For sure.
And speaking of visualizing potential, what else is heavily influenced by this energy landscape?
What's that?
The speed needed to escape a planet's pull.
You mean escape velocity?
Uh-huh.
Isn't that the speed you need to reach
Yes.
to completely break free from a planet's gravitational pull?
Exactly. And it turns out that understanding gravitational potential can help us calculate that velocity.
Okay, so we're going to need to calculate that in the next section, I guess.
Yeah, we are.
Okay, help me connect the dots here. How does understanding gravitational potential help us figure out escape velocity?
Think about it this way. To escape a planet's gravitational pull, you need enough energy to overcome that negative potential energy holding you there.
All right, it's like you're trying to climb out of that gravitational whale we talked about here.
Exactly. And the deeper the more energy you need to reach the top. So if the gravitational potential is more negative, closer to the planet, it would take more energy to escape from there.
Right.
Compared to, say, higher up in orbit.
Okay.
Where the potential is less negative.
Wait, so does that mean escaping from higher up is actually easier? That seems counterintuitive.
It does seem that way.
Yeah.
But that's the beauty of understanding gravitational potential.
Uh-huh.
It reveals these subtle but important aspects of how gravity works.
Right.
And yes, it would take less energy to achieve escape velocity from a higher altitude because you're already starting from a point of higher gravitational potential.
So that's why rockets launch vertically to gain altitude quickly.
Precisely.
They're trying to get to a point where the escape velocity is lower.
They're essentially getting a head start in their climb out of that gravitational well.
Okay, that makes so much more sense now.
Good.
I'm starting to see how this seemingly simple concept of gravitational potential is actually the key to understanding so much about the universe. It's like a secret code.
It really is. And once you understand the code, you can unlock a whole new level of understanding about how objects move and interact within gravitational fields.
So we've talked about escaping gravity's pull. But what about objects that are trapped by it?
Okay.
Like satellites in orbit.
Yeah.
How does gravitational potential play into that?
That's a fantastic question. And it brings us to another crucial point about gravitational potential.
Okay.
It's all about finding a balance between kinetic energy, the energy of motion, and potential energy.
Right. So a satellite in orbit has both kinetic energy because it's moving and potential energy because of its position high above Earth. But how does gravitational potential help us understand that balance?
Remember the equation we talked about earlier, U equals M? It tells us that potential energy is directly related to gravitational potential.
Okay.
So the higher the satellite is above Earth,
Right.
the higher its gravitational potential.
Okay.
And therefore, the more potential energy it has.
Okay, but too much potential energy, and it would just fly off into space, right?
That's right. That's where the kinetic energy comes in.
Okay.
The satellite needs enough kinetic energy, meaning enough speed, to counteract the pull of gravity and prevent it from falling back to Earth.
So it's like a delicate dance between motion and position.
Yeah.
Where the satellite has just the right amount of kinetic energy to balance out its potential energy.
That's a great way to put it. And understanding gravitational potential helps us calculate that delicate balance.
Okay.
It's like knowing the rules of the dance floor, so to speak.
So if the satellite slowed down, it would fall back to Earth?
Exactly. The balance would be tipped, and gravity would win the tug of war.
Wow. I'm starting to see how this all ties together. Gravitational potential isn't just some abstract concept.
No.
It's the key to understanding how objects move and interact within gravitational fields, from rockets escaping Earth's pole to satellites dancing in orbit.
And it goes even further than that. Gravitational potential helps us explain everything from why planets orbit stars in elliptical paths to why black holes warp the fabric of space-time.
Okay, I think we've covered a lot of ground here, and my brain needs a moment to catch up. Before we move on, maybe a quick recap would be helpful.
Absolutely. We started by defining gravitational potential as the energy associated with the location within a gravitational field.
Right.
Remembering that it's always negative with the 0 point at infinity. It's like
Yeah.
a cosmic energy debt.
We also uncovered that surprising fact that the mass of the object being moved doesn't affect the potential at a given point.
Exactly.
Only the source mass matters.
That one still has me scratching my head a bit, but I'm getting there.
It's a tough one. We also touched on how understanding gravitational potential is essential for calculating things like escape velocity,
Uh-huh.
the speed needed to break free from a planet's gravitational pull.
Right.
Right. And we explored how stable orbits are all about finding that delicate balance between kinetic energy and potential energy, like a cosmic dance.
Exactly. You even made that brilliant connection to something that brings us to a crucial point.
You mean my question about dams? I'm not sure I follow.
You asked how this theoretical concept of gravitational potential applies to things here on Earth, and you mentioned dams, which was a fantastic insight.
Okay.
It brings us to the idea that gravitational potential isn't just about the theoretical. It has very real and practical applications in generating energy right here on Earth.
Okay, I'm all ears. How do dams connect to gravitational potential? It still seems like a bit of a leap to me.
Not at all. Think about how dams work. They create a height difference between the water levels, upstream and downstream. That height difference is the key.
So the water stored behind the dam higher up has more potential energy than the water flowing out at the bottom. Is that what you're getting at?
Exactly. And that difference in potential energy is directly related to the difference in gravitational potential between those 2 points.
So we're essentially tapping into gravity's pull to create a flow of energy. That's incredible.
Precisely. When that water is released through the dam, its potential energy is converted into kinetic energy, spinning turbines that generate electricity. It's a brilliant example of how we can harness a fundamental force of nature to meet our energy needs.
Wow, I never thought about hydroelectric dams in that way before. It makes you appreciate how something as seemingly simple as gravity can have such profound implications for our lives.
It really does. And it's not just hydroelectric dams. Think about tidal power, which harnesses the gravitational pull of the moon and the sun to generate energy from the rising and falling of ocean tides.
So we're not just talking about harnessing the Earth's gravity. We're tapping into the gravitational forces of celestial bodies. That's mind-boggling.
It is, and it opens up a whole realm of possibilities for how we might harness gravity's power in the future. Who knows what other innovative ways we might find to tap into this fundamental force.
Okay, my head is spinning with all these possibilities.
Yeah.
Before we get too carried away, let's do a final recap for our listeners to make sure we've tied all these threads together. We started by exploring the concept of gravitational potential, defining it as the energy associated with a location within a gravitational field.
And we can't forget that key takeaway, gravitational potential is always negative, with 0 defined at infinity. It's like a cosmic energy debt.
We also uncovered that surprising fact that the mass of the object being moved doesn't affect the potential at that point. Only the source mass matters. That one still has me scratching my head a bit, but I'm getting there.
And then we dug into how gravitational potential helps us understand things like escape velocity, the speed needed to break free from a planet's gravitational pull.
Right. And we explored how stable orbits are all about finding that delicate balance between kinetic energy and potential energy, like a cosmic dance.
You even made that brilliant connection to hydroelectric dams and tidal power, demonstrating how we can harness the power of gravitational potential to generate energy right here on Earth.
This has been a truly mind-expanding deep dive. I feel like we've gone from abstract equations to a much deeper understanding of how gravity shapes our universe and even influences our lives in very practical ways.
It's amazing how one concept can connect so many different aspects of our world, isn't it?
It truly is. And for our amazing listeners who have joined us on this deep dive, I hope you're walking away with a newfound appreciation for the power and beauty of gravity and its potential, quite literally. Keep those minds curious, and we'll see you on our next deep dive into the world of knowledge.
Until next time.